All right, welcome back. So in this video, we're going to finish up section 4.3. So where we had left off, we were looking at conditional probabilities. Prior to that, we were looking at the complements rule. And I wanted to go back and look at this card problem that we had done before, where we found if we draw four cards from a deck of cards, what is the probability that we get at least one face card? We saw that if we take the complements approach, it's just a couple lines and ends up being about 0.6624. So I wanted to next see what does this look like if we do this directly, because thinking it through, if it's directly, we have to calculate the probability of there being one face card or two face cards or three or four. So there's a couple of possibilities there, and they're all mutually exclusive, right? You can't have simultaneously one and two face cards exactly, right? So those are mutually exclusive, so we need to figure out those four probabilities and add them up. So let's see how it looks if you do it directly. Okay, so same problem, just done directly. So let's kind of go through step by step. So there's the problem. And we saw the probability done directly was 0.6624, just about. Okay, so if we're going to do this directly, we need to figure out the probability first of getting one face card. So the probability of getting one face card is going to be, well, the first one needs to be a face card. There are 12 face cards out of 52 cards. And then this is done without replacement. So there's 51 cards, out of which 40 are face cards. Then for the third draw, there are 50 cards left, out of which 39 are face cards, and then 49 cards, out of which 38 are face cards. Okay, so the first four fractions take into account us getting one face card, and then the other three are taken from the 40 non-face cards that we have. So the thing is that that one face card could occur in the first draw. It could be drawn second, drawn third, or drawn fourth, right? Did the face card come up first? Was it the third card picked? There's four possibilities for where that first or that one face card could be drawn. And so that's why right here we have this multiplication by 4. Okay, and so that gives us about 0.4379. That's the probability of us getting exactly one face card. Okay, so next we need to say, okay, well, what if there's two face cards? If there's two face cards, there's, again, in the denominators, there's 52, then 51, then 50, then 49, reflecting the fact that we're doing our drawing without replacement. But for the first two cards, they're face cards, right? So there's 12 face cards at first, and then only 11, because the first one is assumed to be a face card. And then the remaining two cards drawn have to not be face cards. So there's 40 and then 39. Okay. So that's the number of ways basically of getting two face cards, except that again, those two face cards could be drawn first and last. They could be the first two cards drawn, or maybe the last two cards drawn, or maybe they're the middle two cards. I'll leave it to you to work that out for now, but it turns out that there's 6 ways that, or 6 positions that those two face cards could be in. First two, last two, middle two, and then those two switched. So that doubles, making 6 possibilities. Okay, that's what all this writing is about. Okay, then for 3 face cards, you're getting the hang of this now. There's 52, then 51, then 50, then 49. And then we're doing 3 face cards. So it should be 12, then 11, then 10, reflecting the fact that we're picking from 12 face cards. And this time there's only one non-face card drawn. So that's where that last fraction of 40 out of 49 is. Okay, then we're going to end up multiplying by 4 again, because if we're getting 3 face cards and 1 non-face card, was the non-face card drawn first, second, third, or fourth? So there's 4 possibilities for where that non-face card would go. So that works out to be about 0.032. So that's relatively small. Finally, 4 face cards. It's the same 52 down to 49 in the denominators, and we're only picking face cards this time, 12, 11, 10, and 9. Okay, and this time there's no non-face cards to be chosen, so there's no multiplier. It's only about 0.002 almost, the probability for that occurring. Okay, so now the probabilities we just calculated, they're all mutually exclusive. You can get exactly 1, exactly 2, exactly 3, or exactly 4. You can't have simultaneously exactly 3 and exactly 4, right? So since those are mutually exclusive, we're going to add together the probabilities. So all those 4 intermediate results, we're going to end up adding those 4 probabilities together, and you get 0.6624 just about, which agrees with what we got going indirectly. But as you can see, the indirect approach is way easier. Here, there's of course a lot of writing because I tried to explain it as I went through, but still you'd end up with quite a bit longer calculation doing this thing directly. All right, so hopefully that clears up the question. Let me know if you have any further questions. And then in the next video, we'll be starting up section 4.4, which is about counting methods. In the meantime, let me know if you have any questions, and have a great day.